As global warming intensifies into global heating, we are witnessing a wide range of serious problems around the world. Among these, we focus on access to clean drinking water, especially in developing countries. In developing countries, securing water is difficult, and even when people manage to get water, it's often unsafe, exposing them to harmful bacteria and pathogens. To make matters worse, global warming is further aggravating these problems. In fact, according to a UN water scarcity map, most of the regions suffering from a lack of drinking water are in developing countries. In addition, research on water sources revealed that over 50% of developing countries lack drinking water. That means more than 5 out of 10 people are struggling without enough clean water. So, have there been any engineering efforts to solve the water scarcity problem in developing countries?
Yes, there have been. In 2022, a team of undergraduate students from Gwangwon University's Environmental Engineering Department conducted research to tackle this issue. They announced eco-friendly drinking water purification methods in that there is a lot of sunlight in developing regions and recycling large amounts of waste toner discarded in developed countries into evaporators. Their experiment was successful. The evaporator made by recycling waste toner actually increased water evaporation rates and confirmed that the photocatalyst used in the experiment produced hydrogen peroxide needed for disinfection. But there was one major drawback, which is the size. The device was too large for people to carry and use easily. If you tried to use it, it might look something like this. Focusing on size, we decided to create a portable water purification device that satisfies the following conditions.
First, it needed to be made of small portable materials. Second, use items that are commonly available in developing countries. Finally, we have come up with these designs that satisfy both conditions. First of all, we use two PET bottles, which are already widely available in developing countries. One PET bottle is filled with contaminated water. After that, add a sponge coated with a photocatalyst to purify water, and add an evaporator made by recycling waste toner to increase the evaporation rate. Another bottle collects the water that has evaporated. Now the two bottles are then connected using a special cap we designed, called the water slide. When sunlight hits the bottle, the photocatalyst disinfects the water, and over time, the water evaporates. The evaporated water condensed and moved to the plastic bottle next to it through the water slide. The collected water is now clean and safe to drink. We tested this design to verify its effectiveness.
The evaporator was based on findings from previous research. It was made by recycling black toner waste, which is discarded in large amounts in developed countries. Floating an evaporator made by adsorbing black waste toner and iron onto filter paper increases the photothermal effect. In the process of adsorbing a solution made by mixing waste toner, ethanol, and a small amount of iron on filter paper, use a vacuum pump to adsorb well. For the photocatalyst, we used TiO2. TiO2 is abundant, affordable, stable, and non-toxic. TiO2 is coated on the sponges, and the sponges are cut to fit the PET bottles. Everything is ready. Now we added contaminated water to the PET bottle, inserted the sponge and the evaporator. Now we place the bottles in direct sunlight. We conducted a comparative experiment to confirm the photothermal effect of the waste toner. One bottle contains an evaporator and the other does not. All experimental conditions are the same except for the evaporator.
After 6 days in a sunny outdoor environment, we checked the result. Let's take a look. The bottle with the evaporator produced a visibly larger amount of purified water compared to the one without it. We checked more accurately the amount of purified water produced during the 6 days. About 9.8 milliliter of purified water was produced in the PET bottle with the evaporator, but about 1.9 milliliter of purified water was produced in the PET bottle without the evaporator. This clearly demonstrates the effectiveness of the evaporator's photothermal properties. Next, we tested how well the water was disinfected using TiO2. We measured its sterilization ability by observing E. coli cultures. Before the experiment, the contaminated water was full of E. coli with 158 colonies observed. But after disinfection, the purified water contained no E. coli at all. This proved the disinfection capability of the TiO2-coated sponge.
Overall, our experiment was a success. We confirmed both photothermal effect of the recycled toner evaporator and the disinfection ability of the TiO2-coated sponge. However, we recognized one limitation. The environmental conditions in our experiment were not identical to those in developing countries. In regions with more sunlight and heat, we expect the evaporation effect to be even greater. Our ultimate goal is to distribute the water slide caps and purification kits to developing countries. With just sunlight and this simple kit, people will be able to purify contaminated water wherever they are. The kit includes the water slide cap, some evaporator papers made from recycled toner, TiO2-coated sponges, and an easy-to-follow instruction manual. We've ensured that the kit is easy to assemble and simple to use, so it can be carried and operated anywhere. For many of us, water may be a common resource that can be wasted, but for others, it's not. We hope that there will be constant research on drinking water until the day when clean water is available to all around the world.